Hello everyone, my name is Junaid Mahmood. Today I'm excited to share our ICSE 24 paper titled on using GUI interaction data to improve text retrieval based bug localization. Let's start with different types of software bugs. There are two types of mobile app related bugs. The most obvious type is crash. Here there is a bug that occurs when there is a crash. Crash has stack traces. Even if stack traces are not present in bug reports, developers can reproduce the bug and collect necessary traces. Therefore, it is easy to identify bugs in code. However, it's challenging to describe non-trivial bugs as they are tightly bound with contextual information specific to the app. Let's take a look at an example of a non-trivial bug taken from the Marker app, which is used to create notes and manage to-do lists. Here, we can see a file called test with todo.txt extension, which is the last file created before navigating to this screen. When a user tries to create another file as shown in the right screenshot, the app correctly remembers the extension of the previous file, but the type is marked down. This is the bug. To localize the bug, as the first step, the bug needs to be reproduced automatically or manually. Localizing a bug is a very difficult task because in most cases developers need to be familiar with the underlying source code structures and features of the application. In automated bug localization, potential bug locations are provided as suggestions to developers. To solve that hard problem, prior work introduced several techniques. These techniques utilize different information resources such as execution information from stack traces, code dependencies via source code analysis, or historical information extracted via source code analysis. The commonalities of all those techniques are that all the prior work defined this problem as an information retrieval based bug localization technique. Here, these automated techniques consider bug reports as a query and provide a ranked list of potential bug files according to the textual similarity between bug reports and source code files. Usually, common information used in the query is the bug report title and description. This ranked list of buggy files is not 100% accurate because of the lexical gap between the report and the code. So, is there anything we can do to improve the performance of these approaches further? This is where the goal of our work comes. There are several steps that are required to reproduce the bug, starting from opening the app to the screen where the bug manifests. In all those steps, a lot of screens are traversed and many screens are exercised. We know bugs manifest through the UI. Prior work does automatic bug reproduction, gives the given event trace information, and we are going to leverage those approaches. From bug reproduction information, we can get all the GUI information from the initial screen of the application to the screen where the bug manifests. This information is a kind of representation of where the developers start the localization process. We wanted to know if leveraging that information would improve information retrieval based localization performance or not. To achieve that, we designed a study. The goal of our study is to determine which GUI information we can use specifically and how to use this information to improve localization. In this study, we are bringing a new type of information, that is GUI interaction information. We applied different types of GUI information to existing two augmentation techniques which are used to reduce the lexical gap. I will describe those in the later slides. To evaluate the performance, we constructed a new dataset and applied that in four information retrieval based techniques, namely bug locator, Lucene, Unix coder, and sentence BERT under various configurations. So what type of GUI interaction information are we going to use? As I said earlier, automated reproduction techniques will provide an XML-based reproduction trace. Using this type of trace, we can get two types of GUI information from a screen. First one is activity name. Each GUI screen corresponds to one activity name, and if pop-up information is present, we can also get window information. The second one is resource ID of any component on that screen. For example, here plus button corresponds to the resource ID fab add new item. Now, how can we use this information to find the files related to a given screen? There are mainly three types of related source code file types. First one is GUI screen. To find the source files related to this particular screen, we first identify the activity name of that screen. Each activity name corresponds to one Java file in the repository. So we'll search for Java files that have the same name as that activity. The second one is the files related to the GUI components of a screen. Assume we need to find the related Java file for a quick note component, which is highlighted in the green box here. For that component, we first identify its resource ID and then search for event listener methods that use that resource ID. Now we know which Java files contain this event listener, and that will be related to that component. Since there could be multiple components on a screen, there will be multiple component related files for a single screen. We will identify all the files that are related to the GUI screen components and consider those as potential locations for bugs. Exercise GUI components are also usual GUI components. The only difference is that these are exercised in the reproduction steps of the bugs. For example, the second str create another new file in this bug report corresponds to red fab button on the screen. We can use the same procedure to find bug related files as I described in the previous slide. In this particular example, we found that the event listener of the exercise GUI component IDs is present in main activity.java file. Therefore, we consider this file as a potential location for bugs. Note that in this project, we did not consider XML files. Rather, we considered Java files as potential bug locations. We first utilize the GUI information in query reformulation. For a given bug report, we first perform the pre-processing. We pre-process the bug report using common steps like removing punctuations used in past information retrieval work. Then we add GUI information for query expansion. We also replace the bug report in the query and utilize only the GUI related information, which is called query replacement in our approach. The second augmentation technique is called re-ranking. One way of re-ranking buggy files is filtering. In a particular corpus, a few files are related to the GUI and others are not. In filtering, we will exclude the source files which are not related to the GUI. Another way of re-ranking is boosting. For example, here the three files marked in light yellow are related to the GUIs and two files marked in green are not related to the GUIs. Here we will not exclude any files but boost the rankings of the GUI related files compared to the other files. The third re-ranking technique is filtering plus boosting. Here we first filter out unrelated GUI files and apply boosting to that less restrictive set. We studied various configurations under 4 different parameters. We studied 2 to 4 GUI screens including the buggy screens. We used 5 different combinations of GUI interaction information. We used 2 query reformulation techniques, specifically query expansion and query replacement. We also used 3 re-ranking techniques, that is filtering, boosting and filtering plus boosting. In total, we used 657 configurations of GUI information for each baseline. As we use 4 baselines, we use 2628 configurations in total across all experiments. In our study, we asked 3 research questions. First one is effectiveness of using GUI interaction information from different number of screens. The second one is effectiveness of the type of GUI interaction information and augmentation method. The third one is overall best performing combinations of using GUI interaction information. For our empirical study, we constructed a new dataset for evaluation purposes. We selected 80 bug reports from 39 mobile applications from the Android 2 dataset. 3 authors of the paper first independently reproduced those bugs and extracted buggy Java files, screenshots, metadata, and event execution data. Then they discussed and resolved if there were any disagreements to derive the final dataset. We selected 4 information retrieval-based techniques. The first 2 are traditional, that is bug locator and Lucene, and the last 2 are neural language models, that is SentenceBird and UniXcoder. The first one is bug locator, which is a revised vector space model. Bug locator ranks longer documents higher, assuming that these are more likely to contain bugs. The second one is Lucene, which is also a vector space model and uses TF-IDF. The third one is UniXcoder, which is a multi-layer transformer architecture pre-trained on the code SearchNet dataset. This model exhibits great performance in code understanding tasks. The final one is SentenceBERT, which is a modification of the pre-trained BERT model and fine-tuned on a natural language inference dataset. This model augments the traditional BERT model with Siamese and triplet networks, allowing for better support of tasks such as clustering and semantic search. As the first research questions, we wanted to know the number of screens that give the best performance. We find that using GUI information from the buggy screen and two preceding screens provides the highest overall increase in effectiveness. For three screens, the average hit at 10 improvement is 7.29%. So, what is the learned lessons from here? GUI information from the buggy screen and two preceding screens provide the highest overall increase in effectiveness. Therefore, relevant GUI information for bug localization is contained not only in the buggy screen but also in the preceding screens. Also, we wanted to know what the impact of GUI information types is. If we apply filtering to the screen components, the performance improves for three techniques except Unix coder. However, the improvement is not much. Boosting exhibits great performance across all techniques. For all baselines, we have seen improvements of around 9 to 15%, and the biggest improvement for SentenceBERT is for SentenceBERT, which is 15.52%. We get the best effectiveness for boosting when you use GUI screens or GUI screens plus exercise GUI component information types. For filtering plus boosting, we have seen improvements in all techniques. Filtering with screen components and boosting with GUI screens or GUI screens plus exercise GUI components performs best across all the baseline techniques. The best improvement for boosting is 15.52%, which we get for SentenceBERT. We find that query replacement generally does not lead to improvement over the baseline. We observe slight improvement for bug locator and Unix coder. Query expansion does lead to improvements, and the improvements is the highest for Unix coder. We did not observe any improvements for SentenceBERT. We speculate that this improvement for Unix coder may be due to the fact that embedding file names into Unix coder's code-specific embedding space makes it far more likely for those files to be retrieved than other techniques. Then we analyze the performance of query reformulation separately. As shown in the box plot, compared to query replacement, query expansion shows improvements across all the localization techniques. This table shows that combining query expansion with the screen components or GUI screen information resulted in the highest improvement. For query replacement, we did not observe many improvements. Next, we analyze the performance of each re-ranking technique separately. If we apply filtering, the performance will not be good across all the techniques, but compared to the filtering, boosting shows improvements. When comparing the medians, we can see that filtering plus boosting shows the highest performance across all baselines. Filtering with the screen components and boosting with GUI screens plus exercised GUI components resulted in the highest effectiveness. So what have we learned from here? Query expansion is better than the query replacement, and filtering with information types that map to screen components or GUI screens and boosting with information types that map to GUI screen or GUI screen plus accessed GUI components tend to give the highest improvement. For RQ3, we investigated the best performing configurations for each technique. These were selected by taking the top performing techniques according to heat set 10 and breaking ties according to heat set 5. Leveraging GUI information has improved performance across all techniques, resulting in 12.5 to 18.3% increase in heat set 10. Filtering with screen components or screen components plus GUI screens and boosting with GUI screens plus GUI screens or GUI screens plus exercised GUI components exhibits the best performance. This is the learned lessons from RQ3. Here, the best GUI augmentation method is filtering plus boosting, and the best performing configuration utilizes the following GUI information types, that is filtering with screen components or screen components plus GUI screens, and boosting with GUI screens or GUI screens plus exercise GUI components. Here, the best improvement is for HitSet 10, range from 12.5 to 18.3%. In summary, we have addressed the limitations of existing information retrieval-based bug localization. We designed a study to investigate if GUI information can be utilized to improve existing text retrieval-based bug localization. We released a new dataset on text retrieval-based bug localization. We have proven that integrating information from GUIs improves existing text retrieval-based bug localization. We have released all of our data and source code. We suggest that those interested to check out our replication package. Thank you, and I'm happy to answer any question.